All right, so let's go ahead and get started. I'm not sure why the room is dark. Maybe it's because the air conditioning doesn't seem like it's working. And maybe they're trying to help keep us cool. But what I want to do is try to take a look at a few more Nyquist stability examples. These particular examples will illustrate some cases where the computer tool is not quite as straightforward as one would think. Okay, we did a few examples last time we met and just showed how the computer tool can be used to generate the Nyquist plot, and then we could analyze Nyquist stability. But today I want to look at two examples where a little bit of work is, or a little bit of care is required on our part. Now, as I mentioned last time we met, there will not be a live meeting on Friday. There will not be a live meeting on Friday. And if Canvas is working correctly, you should be receiving an announcement this morning to take a look at some videos. So the admin, there is no class meeting Friday. And I encourage you to take a look at a few Panopto recordings. The Panopto recordings I recommend you take a look at are number 24, A and B. I broke the lecture up into two parts, and number 25, A and B. All right? So that's for Friday. Today, what I want to do is go again over a couple of Nyquist stability examples. And let me first review this technique. With Nyquist stability, what we do, this technique allows us to predict control system stability Control system implies feedback. Okay. Feedback means there's a loop involved. Okay. So we are able to predict the stability of a control system using only the so-called open loop model. Okay. So we use the open loop to predict the stability of the closed loop. All right. So we plot the frequency response. And then we have this criterion that we have to analyze. It says Z is equal to N clockwise plus P. And you can take a look at your notes from last time. Remember, P is the number of open loop poles. Number of open loop poles in the right half plane. It's not the number of poles, it's the number of poles in the right half plane. Open loop. And this is going to be clockwise encirclements of the point -1 in the frequency response plot. And this then is the number of closed loop or feedback system poles in the right half plane. Okay, so this is what we covered last time. Just kind of summarizing this. Just as a reminder, we've got three numbers here, Z, N, and P. P and Z, these are two numbers that are greater than or equal to 0. They can never be negative. So it's N that can be negative. Okay? N can be negative. All right, so let's do a few examples. Let's first do an example that has no complications. This is a problem with no complications. Okay. Oh, why is it upside down? When did it become upside down? All right. I think this is God telling me to retire. Technology is just getting the better of me. All right, so this is our control system we're going to try to figure out. I would hit the machine, but I don't think the electrons will respond. Still upside down. All right. So the open loop is 4 over s plus 1, s plus 2. Okay, that's the open loop. I'm going to try one more thing. I'm going to turn the projector off and turn it back on and see if that works. Nope. I don't see an invert button or a flip button. I think it's oh great. Now this thing has a mind of its own. We'll do the best we can. We'll go a little slower than we need to, but that's the open loop. Okay, so it's not just this box alone. You have to take into account everything in the loop. All right, but we're not calculating the closed loop model. Okay, so let's enter that into MATLAB. I'm just going to call this G. Okay, I'm going to call this model G, G of S. All right. So in MATLAB, I'm going to say G is a transfer function. The numerator is 4, and the denominator is s squared plus 3s plus 2. Okay. And then what we're going to do is we're going to type in the word Nyquist. G. And it's going to generate a Nyquist plot for us. I'm going to try to draw upside down here. And if we take a look at this, I think it's going to look something like this. It's going to look something like, I think it's going to start off here at 2. And it's going to wrap around like this. And then it's going to do the negative frequency, something like this. And then the point -1 is going to be right here. Okay. Take a moment and right-click in the screen here. You might do a right-click. And do a right-click and turn off the negative frequencies. You know, there's a sub-menu called Show, and turn off the negative frequencies so you can reinforce in your mind that part of the curve on the Nyquist plot is the positive frequencies and part of it is the negative frequencies. All right, and you see this. Okay. Is this kind of what you're seeing? Okay, so let's go ahead and apply Nyquist criterion here, and let's do n. N is going to be the number of times this thing encircles the point -1. That's going to be 0. We have to do p. P is the number of open loop poles that are in the right half plane. So this thing has 2 poles, but this is at s equal to -1. That's not in the left or right half plane, and neither is this one. So p is equal to 0. And so when I add those 2 numbers, I get z is equal to 0. So the prediction is that this closed loop system is going to be stable. Okay. And just to check, let's use the computer to check rather than doing it by hand. Let's calculate the closed loop model and do a step response and see if it's okay. So I'll do something like this. Let's create a new model called H. I'm going to create a new model called H. Okay, a new model called H, and it's going to be the closed loop model for this system. And since I have G, I can use the feedback command to calculate it. I'll say feedback G comma 1. So let's do this. Come on. Use the feedback command to calculate the model of the closed loop system. We already have the model of the open loop, which is G. So the forward gain is G from here to here. And the feedback gain is 1. So that's what this is. The forward gain is G. The feedback gain is 1. So we'll calculate it. And then what we can do is let's do a step of H. Let's let the computer simulate that for us, and it should show a stable response, a bounded response. Okay? So it's a very straightforward example. Okay? Now let's take a look at some examples where things are a little bit more complicated. Okay, so this is going to be example number 2. This is going to be example number 2. And example number 2 is going to be complicated because it's going to have a pole on the imaginary axis. Okay, it has an open loop pole on the imaginary axis. All right, so this is going to be the system we're going to look at. It's very simple, but it illustrates a problem that we have. Matt, if I stand on this side and write backwards, is that going to mess you up? Because you're looking at the screen. Okay. All right, so I'm going to stand this way. All right, so this is the problem that we have. This is the open loop model, and it has a pole on the imaginary axis. So let's first go ahead and do the open loop model. We'll say G is a transfer function. The numerator is 2, and the denominator is just S. So you do it like this. Okay, S. There is no constant term. And then let's do a Nyquist plot. Okay. Now you may remember, what does the Bode plot look like for 1 over S? The Bode plot for 1 over S, the magnitude is really large when S is small. When S is small, when S is 0, you get 1 over 0. So the gain is infinite. And then when omega is real large, the magnitude gets small. But the phase, S is equal to j omega, the phase is always negative 90 degrees. And so with that knowledge, we can sketch the Nyquist plot real quickly, and you'll get something that looks like this. Okay, there's the Nyquist plot. This is the real axis. This is the imaginary axis. And the point here is -1. Okay. All right, so let's apply the Nyquist criterion. What is P? P is the number of poles in the right half plane. How many poles are in the right half plane? Let's have a little discussion here. 1. 0. Okay. You two argue it out. Why do you think it's 1? The pole is 0. Okay. Why do you think it's 0? Let's have a vote. Okay. Does anybody think it's 2? Nobody thinks it's 2. Okay, so it's 1 or nothing, right? So raise your hand if you think it's 0. 1, 2, 3, 4, 5. Raise your hand if you think it's 1. 1, 2, 3, 4, 5. Okay. It's kind of, we got a divided decision here. Reality is it's ambiguous. Is it in the right half plane? The definition says P is the number of poles in the right half plane. So, your mom says, stay in the yard. And you decide to go and you put 1 foot over in the neighbor's yard. So are you being disobedient or not? It's only 1 foot in the neighbor's yard. My other foot is still in my yard. So it's ambiguous. Okay, this is a problem. Is it 1 or 0? I'm not sure. Let's talk about n. How many times has this thing encircled the point -1? Okay. Somebody says 0. Well, the thing is, all right, does the plot show these arrows like this? Okay, so here it is. The two ends are not closed. So is the plot really going to go this way, or is it going to go this way? To join the ends? I got to join the ends. I don't have a closed plot. So again, this is ambiguous. All right. So we need to do a little bit of engineering to try to make this tool useful to us. Okay. So rather than analyzing this exact problem, let's change the problem a little bit. Let's try to analyze a very near problem. It's almost the same problem, but it's not quite the same. Okay. So compare this diagram to the previous one. This is the original model that we have. This could have been the model, say, for speed control of a vehicle. So this could be like force, and this is speed. Okay. This is almost that. Epsilon here is a parameter. Epsilon is a small number. Hey, would anybody like to suggest a small number?
2.
What? 2? Okay. I would say that two is not very small. I mean, 2 is not very small. We got other numbers in the model that are already, of that size. 0 would just put us back to where we were. Okay. The 2 males in the room have spoken. Let's hear from a lady. What do you suggest for a small number? 0.1. 0.1? 0. A tenth, 0.1. Okay. Okay. So redo the problem. Redo the problem. Now you're going to get with 0.1, the Nyquist plot is going to look like this. Again, I'm going to label this time now using polar coordinates. This is 0 degrees, 0.1. This thing is going to start off at, I think, 20 out here. It's going to wrap around like this. Minus 1 is out here. Is that what y'all see? Somebody's shaking, saying no. Are you seeing this or not? Some of you are saying yes. Okay. You should be something. So my claim is this is a very near problem to this. And the claim is if I kind of zoom in real close here, zoom in real close here, this is starting to look a little bit like this. Okay. I can make it look even closer to it by making this number even smaller. Maybe I'll try not 0.1, but maybe 0.01. Okay. So the whole idea is if you have a problem like this, maybe you can analyze a near problem. Now let's analyze this near problem and see if we have resolved our ambiguities. In this near problem, what is P? P is 0. It's clearly 0. It's clearly, I mean, the pole is close to the imaginary axis, but it's clearly in the left half plane. Yes, question? Okay, so the question is, could epsilon be a negative number, right? That's another way. I think we have enough time. We'll try that. All right. So hold that thought. But let's do this one first. P is equal to 0, so there's no ambiguity. How about the ambiguity regarding the encirclements here, n in the clockwise sense? Again, there's no ambiguity. It's been removed, right? And so z is equal to 0. So the near problem says the system should be stable. This is a simple enough problem. We can also check it by hand. I'll let you do that over lunch break. Now let's go back to was it Jonathan who asked the question? How about epsilon negative? Okay, let's do a negative number. So what we'll say is G is a transfer function. The numerator is 2, and the denominator is 1 minus epsilon. Okay, let's do it this way. A negative epsilon. Still a small non-zero number, but it's negative. So the question is that going to come up with a different result? So let's take a look and see what that does. I'm going to sketch this out of the top of my head. It's going to start off the plot's going to look something like this now. And this is going to be negative 20. And I think the arrows are going to go this way. I'm just thinking off the top of my head. Okay. Let's go through and apply Nyquist criterion. What is P in this case? P is 1. Does everybody see that? Because I made epsilon a negative number, this is now a pole in the right half plane. My near approximate model is different than the previous one, and so my P is different. What is N in a clockwise sense? Negative 1. Okay. Anybody have any questions about that? Okay, and because today is Wednesday, the best day of the week, we can do this algebra well. So Z is equal to 0. So again, this approximate model also predicts that the control system will be stable. So the conclusion is it doesn't matter whether you use a positive or negative small number, as long as you apply the rest of the tools correctly. All right? One more problem for the day. This thing in the box here, the process is the same thing as s squared plus 2s plus 1 divided by s squared minus 2s plus 1. Okay. So let's enter this model into MATLAB. G is a transfer function. I got a 2 here, so I'm going to say 2 times this. The numerator is going to be 1, 2, 1. So it's 2 times 1, 2, 1. Oh, that's not very good handwriting. Put a little space there. It's not 21. It's 1, 2, and 1. And then the denominator is 1 minus 2 and 1. Let me write that a little better. Let's do a Nyquist plot. Okay, what is P? P is 2. Okay, 2 poles in the right half plane. And in the clockwise sense. So our conclusion is that the control system is not stable. Okay? Let's verify this with a computer. Let's calculate the closed loop model. Let's calculate the closed loop model. Okay. That's what it is in theory. Let the computer do it. Let's use the feedback command to calculate it. With the feedback command, I have to give it the forward path gain from here to here. So that's G, the G that I defined earlier. And the feedback gain is 1. And now let's do a step response on H. It blows up, right? Yes? Did it blow up? Did the response settle out or did it blow up? It settled out. So is this a stable response or unstable response? This is a stable response. Wait a minute. What's going on here? It's supposed to blow up. It's a stable simulation. Okay, but Nyquist said unstable. So let's review again. Did we get one of these numbers wrong? P, number of poles in the right half plane. Does anybody think that maybe we miscounted this? How about N? Stare at that plot. Okay. Right-click in the picture and turn off the negative frequencies. Right-click back in the picture and turn the negative frequencies back on. Go back and forth several times. What conclusion can you draw? Can you say that louder? Okay, so do you see a difference between turning the negative frequencies on and off? One of the arrows disappears, right? The negative frequency arrow disappears. And all that's left is the positive frequency arrow. But the plot doesn't look like it changed anything. So your conclusion probably would be, it's Nicholas, right? Nick? What? Alex, I'm sorry. Said that the negative frequencies and the positive frequency plot are on top of each other. So what looks like this circular plot is actually two plots. The full plot is two plots. The positive frequency is this, and then when you add the negative frequencies to complete the plot, you go around it again. Okay, study carefully and clockwise. Okay, review it again. Okay, so in this particular case, positive omega plot, positive omega, and negative omega plots, these two plots are on top of each other. So if that is the case, we thought that n clockwise is equal to -1. Now that we have this additional piece of information that the two curves are on top of each other, what will we say about this? It would probably be -2. Okay. There's two curves. So this is the hazard of using a really accurate computer. It's sometimes we miss a tiny little detail. So P is equal to 2, N is equal to 2, Z is equal to 0. So this is actually a stable system. All right? That's all I have for today. Let's stop there. I'll stick around for any questions you may have.